Hi students, good evening. So in today's class, we are going to discuss about the application part of chemical kinetics. So before going to the application part of chemical kinetics, I want to discuss about the CPP question which I have asked in the earlier class. And this particular question, most of you have done wrong. So let me. So the threshold energy value is high, hence the energy of activation is also very high. So the energy of activation is very high, hence, so for an endothermic reaction, the energy of activation will be greater than the delta H value. That is the correct answer here. You can see from the graph, it has high value of energy of activation. Whereas on the other hand, if I take exothermic reaction, for an exothermic reaction, the energy of activation, if I take this as reactant and this as product, so the energy of activation will be very less for exothermic reaction. Hence, for this particular question, the correct option is C. So this was the question which I asked in the last class. Okay. So coming back to today's goal, students, today I am going to discuss about the rate constant order of reaction application part. That is, we are going to discuss problems based on these concepts, which is very important. Okay then. So let's go to the problems. The first problem here is, which I have given, for the reaction, reactant R is converted into product P. The concentration of the reactant changes from 0.03 molar to 0.02 molar in 25 minutes. Calculate the average rate of reaction using unit of time both in minutes and seconds. Students, the data which they have given here, so the concentration of the reactant changes from 0.03 molar to 0.02 molar. Initial concentration of the reactant, I take it as R1, it is 0.03 molar, and the change in the concentration, I take it as 0.02 molar at a time interval of 25 minutes. Now I want to calculate the average rate of reaction. So with respect to reactant R, I can write it as average rate of reaction, change in the concentration of reactant R with respect to change in time interval, which will be equal to, so the change in concentration, that is R2 minus R1 divided by time interval, that is T2 minus T1. So the initial concentration of the reactant is 0.03 molar. The change in the concentration of the reactant at a time interval of 25 minutes is 0.02 molar. So R2 is 0.02 molar minus R1 is the initial concentration, that is 0.03 divided by the time interval. So it will be T2 is 25, T1 is 0, so we can take it as 25 minutes. Here you can see the change in the concentration of reactant, that is the rate of reaction, I can write it as minus dr by dt. So if we simplify this, we are going to get the answer as 4 into 10 power minus 4. That will be the answer, 4 into 10 power minus 4 molar per minute. The unit is very important, students, here. So, here we have calculated the average rate of reaction in terms of minutes. Now, in the same problem, let us calculate with respect to the seconds. With respect to seconds. Students, if I want to calculate the rate, average rate with respect to seconds, just so 25 minutes, you convert that into seconds. If you want to convert that into seconds, multiplied by 60. We know that 1 minute will be equal to 60 seconds. So, if you simplify this, you are going to get the answer 6.66 into 10 power minus 6 molar per second. So, this is the answer for the first problem. In this problem, we are calculating the average rate of reaction using unit of time both in minutes and seconds. Okay then. Students, let us go to the next problem. Okay. Students, the second problem, they have given reactant A, reactant B to give product C and D. The rate of disappearance of B is, they have given 1 into 10 power minus 2 mole per liter per second. What will be the rate of reaction, that is with respect to B, and the rate of change in the concentration of A and C. Again, we need to calculate the rate of reaction with respect to B and also the rate of change in concentration of reactant with respect to A and C. For the given equation, let us write the rate expression. So, rate will be equal to, for concentration of A, I can write it as dA by dt. Students, here negative sign implies that the concentration of reactant A is disappearing with time, which will be equal to, with respect to B, I can write it as minus 1 by 2 into change in the concentration of reactant B with change in the time interval, which will be equal to, for product C, I can write it as 1 by 3, I need to divide the stoichiometric coefficient, 1 by 3 into change in the concentration of product C, which will be equal to, with respect to D, I can write it as 1 by 2 into change in concentration of D. Students, here they have given rate of disappearance of B. Now, with respect to B, I can write the rate of disappearance of B. So, rate will be equal to minus 1 by 2 into dB by dt, that is change in the concentration of B by bt, which will be equal to, so 1 by 2, here I can, because rate is negative, so I can take it as positive 1 by 2 into, so the rate of disappearance of B they have given, that is 1 into 10 power minus 2 mole per liter per second. If we simplify this, then we are going to get 0.5 into 10 power minus 2 mole per liter per second. Student, this is the rate of reaction with respect to the reactant B. They have given the rate of disappearance of B. Now, we need to calculate the rate of change in concentration of A and C. You can see that with respect to A, I can write it as the disappearance of A, that is minus dA by dt, will be equal to the disappearance of B, that is minus 1 by 2 into dB by dt, which will be equal to, we know that with respect to disappearance of B, we have calculated. So, the disappearance of A will be equal to, after disappearance of B, which already we have calculated, which will be equal to 0.5 into 10 power minus 2, it is mole per liter per second. This is with respect to A, the second part of the problem. Again, now we need to calculate what is the rate with respect to the concentration of C. Now, let us equate with respect to C and B. We can write with respect to C, that is change in concentration of C will be equal to minus 3 by 2 into rate of disappearance of B. Students, we are equating the equation with respect to C and B here. Now, dC by dt will be equal to, it is minus 3 by 2 into, so they have given the concept that is the rate of disappearance of B, that is 1 into 10 power minus 2. If you calculate this, you are going to get the final answer as 1.5 into 10 power minus 2 mole per liter per second. Students, in these type of problems, you need to just write the rate equation, instantaneous rate, average rate equation or instantaneous rate equation according to the problem, the data which they have asked. Then you need to equate the reactions with respect to their stoichiometric coefficient and you need to work out. This is the important problem. This is based on the rate of reaction. Okay then. Next problem. A reaction. Again, students, before going to the next problem, I think it is the time to ask a context question. And today's context question is an example of blackening of white lead upon prolonged exposure to air. Option C, rusting of iron in moisture. Option D, glowing of charcoal. An example of photochemical reaction. Okay then, so this is today's contest question. And students, yesterday's contest winner is Dhruv Dikshit. So Dhruv, you will get one autumn session free. Congratulations. Okay then. So coming back to the okay then. So coming back to the problems. So now it is the problem number 3, third problem. A reaction is second order with respect to a reactant. How is the rate affected if the concentration of reactant is doubled and second one is it is reduced to half. Let us consider a reaction in which reactant A is converting into product P. Let us consider a hypothetical reaction. And the order of reaction they have given in the problem, students, it is second order reaction. Let us write the rate expression for this. So we know that with respect to A, rate will be equal to K into concentration of A. Students, let the concentration of A is raised to a suitable power X, where X is the order of reaction. Okay then. So now they have given the order of reaction, that is X, we can equate this to 2. Now in the problem they have asked, how is the rate of reaction affected if the concentration of reactant is doubled? Okay then. So let us write rate will be equal to K into, we are doubling the concentration of reactant, that is A becomes 2A, and I have told you that the stoichiometric coefficient X will be equal to 2, that is the order. So they have given in the problem. So rate will be equal to K into, that is 2 square means it is 4A square. So we know that this is the answer here. The rate of the reaction increases by 4 times to its original rate. Again in the same problem, they have asked what happens to the rate if the concentration of the reactant A is reduced to half. Again let us write rate will be equal to K into the concentration of reactant A is reduced to half, where we will get rate will be equal to K into 1 by 4 A square, nothing but the rate decreases 1/4 time of its initial rate. Little bit application based, a little concept is required to solve this type of problems. Okay then. Students, fourth problem. For the reaction A to B, the rate of reaction becomes 27 times when the concentration of A is increased by 3 times. What is the order of reaction? Again, the problem is based on the order of reaction. Let us write the rate equation with respect to reactant A. Rate will be equal to K into concentration of A. Let the order with respect to A, let us take it as X. In the problem they have asked, the rate of reaction becomes 27 times when the concentration of A is increased by 3 times. So, the rate increases by 27 times when the concentration of reactant A is doubled. So, A becomes 3, I have written, because the concentration of A is increased by 3 times, students. Now, 27, I can write it as 3 cube will be equal to, just I write it as 3 to the power of x. Equating the base, we can write it as x will be equal to 3. So, this is a third order reaction. I repeat, so the rate of the reaction increases by 27 times if the concentration of reactant A is tripled, they have asked. So, 27 is nothing but 3 cube I have taken, so will be equal to 3 to the power of x. Here equating the base, we can write x will be equal to 3. So, this is a third order reaction. Yes, Dhruv, it is correct. You are correct. It is third order reaction. Okay then. So, this type of problems, little bit, if you know, if you have understood the concept, easily you can tackle this type of problems. Okay. So, students, next question. The time required to decompose SO2Cl2 to half of its initial amount is 60 minutes. Calculate the rate of the reaction. Student, this problem is based on half-life time. Here they have given the half-life time for the decomposition of thionyl chloride. So, T off they have given, which will be equal to 60 minutes. Then they have asked us to calculate the rate constant of the reaction. So, K value we need to calculate. So, we know that the formula to calculate half-life time, that is T off will be equal to 0.693 divided by K. So, here we need to calculate rate constant, K will be equal to 0.693 divided by T off. So, if you calculate this, you are going to get K will be equal to 0.693, T off they have given 60 minutes. What is the answer, student? Fast. Let us see who will tell the correct answer. Do the calculation fast. Come on. 0.693 divided by 60, and I want you to tell the unit also. I will give just 15 seconds. Any of you, can you calculate and you tell me the value with the unit? Writing the proper unit is very important, students. Come on. Yes. I am not getting any answer. It is 0.693 divided by 60, a simple problem here. So, the answer is 1.155 into 10 power minus 2. What is the unit, students? At least you tell me the unit here. Half-life time they have given in minutes. What is the value unit for K? Yes, it is per minute. The unit is per minute. Students, writing the unit also very important. So, this is the answer for the fifth problem. Okay then. So, the next problem. A first order reaction takes 40 minutes for 30% decomposition. Calculate half-life time. This is the problem they have asked. So, they have given the time T it is 40 minutes. 30% decomposition. Since they have given 30%, percent means per 100, let us take initial concentration R naught as 100%. R naught is 100% here. Let X be the change in the concentration at a particular interval of time, that is they have given 30%. Students, this problem is based on here two important formulas we need to use. One is K will be equal to 2.303 divided by T into log of R naught by RT. This is the formula. Students, can you guess which equation is this? This is the integrated equation. In the regular class, I have derived it, and this is the integrated equation for the first order reaction. Here the initial concentration they have given, students. R naught is the initial concentration. Here RT is the concentration of reactant at that particular interval of time. So here RT can be written as, it will be 100 minus X, that is 100 minus 30. That will be the R naught. Okay then. So now you need to work out this problem. Substitute the data in the equation. K will be equal to 2.303 divided by time they have given, it is 40 minutes, into log of initial concentration of the reactant, students, it is 100%, and RT is the change in the concentration of reactant at the change at that particular time interval. When time is 40 minutes, the concentration of reactant R is given as RT, that is 100 minus 30, that is 70. Now you need to simplify this. Come on, any answer for this? So if you simplify this further, you are going to get K will be equal to 2.303 divided by 40 into log of, here if you simplify this, that is you are going to get 1.428 log of 1.428, you need to find out. So K will be equal to 2.303 divided by 40 into log of 1.428 value, students, it is 0.1548. If you simplify this, you are going to get the answer 8.91 into 10 power minus 3 per minute. Student, this problem is two step. In the first step, we have used the first order integrated rate equation and we have calculated the rate constant. This is the first part of the problem. The second part is we need to calculate off lifetime, and you know that T off will be equal to 0.693 by K. So T off will be equal to 0.693 by K. 0.693, the value of rate constant we have calculated, 8.91 into 10 power minus 3. So T off will be equal to, that is 77.78. So that is minutes. Here rate constant is per minute. So the final answer will be 77.78 minutes. So two-step problem here. In the first step, we have calculated the rate constant, and in the second step, we have calculated off lifetime. Yes. Let's go to the next question here. Show that in a first order reaction, the time required for 99.9% of the reaction to take place is about 10 times then that required for the half of the reaction. Students, we need to show that T 99.9% will be equal to 10 times T off. This is what we need to prove in this problem. So let us write for a first order reaction with respect to 99.9%, the rate equation can be written as, so we know that K will be equal to 2.303 divided by T into log of R naught, sorry, one minute. it is R naught by RT. Okay then. So here let us rearrange this, the time for 99.9%. T 99.9% will be equal to 2.303 divided by K into log of that we need to take, it is 100 divided by initial concentration per percent. Percent means per 100 students. 100 divided by 100 minus. So the change in the concentration RT we can take it as R naught minus X. R naught is 100 minus 99.9%. So T 99.9% will be equal to 2.303 divided by K. If you simplify this, what is the answer you are going to get? That is log of 100 divided by 100 minus, that is 99.1, you are going to get 0.1 here. So totally it will be log of 10 power 3, which you are going to get 3 here. So I am going to do it directly, students. Here log of this is 10 power 2, this is 10 power minus 1, it becomes 10 power 1 if it go to numerator. So totally it becomes 10 power 3. So that is log of 10 power 3 is 3 log 10, nothing but 3. So T 99.9% will be equal to, so you are going to get 6.909 divided by K. Let us consider this as equation 1. Now let us take the equation for half lifetime. We know that T of will be equal to 0.693 divided by K. Let us consider this as equation 2. Now let us divide equation 1 by 2. What is equation 1? It is T 99.9% will be equal to, it is 6.909 divided by K divided by T of will be equal to 0.693 by K, or which can be written as T 99.9% divided by T of will be equal to 0.60909 by K into K divided by 0.693. Send it to numerator. So T 99.9 by T of will be equal to 6.909 divided by 0.693. So you are going to get, if you simplify this, T 99.9 will be equal, sorry, I will write in the next. T 99.9% divided by T of will be equal to, so you are going to get 9.9, which is almost, we can take it as 10. So T 99.9% will be 10 times the half-life period. This is how we are going to prove this. So little bit lengthier problem here. So first we have calculated the time for 99.9%, then that we have taken that as equation 1, then we have taken half lifetime equation. On dividing equation 1 by 2, so we are going to get the final answer, students. Okay then. Let's go to the next problem. The following data were obtained during the first order thermal decomposition of SO2Cl2 sulfonyl chloride at constant volume. Students, if you go through this equation, you can see that, so the reactant and products, they are gaseous in state, and decomposition of SO2Cl2 follows first order kinetics. So let us see what is which is the equation we need to apply. Students, one equation I have derived. This is the rate constant for the first order equation. If the reactant and products, if they are in vapor state or gaseous phase, the equation is P naught divided by 2 P naught minus Pt. This is the equation, student. So in the problem, they have given the time is 100 time is what they have given in terms of seconds. Okay, 100 seconds. Then they have given the initial concentration, initial pressure, that is P naught, which is 0.4. Then they have given Pt, that is change in the pressure, that is 0.7 from the data which is available there. So substitute this in the formula. K will be equal to 2.303 divided by 100 into log of P naught is 0.4 2 P naught is nothing but 2 into 0.4 minus 0.7. So, you are going to get K will be equal to 2.303 divided by 100 into log of, that is 0.4 to 0.8 minus 0.7, it is 0.1. If you simplify this, the final answer will be K will be equal to 2.303 divided by 100. So, log of 0.4 you are going to get 0.6021. So, K will be equal to 1.386 into 10 power minus 2 per second. So, this is the final answer, students. So, these are the problems which I have worked on the concepts like rate, rate constant, order of a reaction, off lifetime, and rate constant for first order reaction in vapor state, as well as the regular equation which we have derived. Okay then. Students, with this I conclude today's class by saying that work out more problems to understand the concept better, and I have given 10 CPP questions. I have given 10 CPP questions. You need to answer those CPP questions, and also the summary for which I am going to just for today's class is rate, rate constant, order, reactions and its applications. CPP. Yes, students, I have given 10 CPP questions. Passport users, you can go through these questions, answer all the questions so that you can understand the concepts effectively. Work out more number of problems. All the best.